Electrical load calculations are a fundamental aspect of electrical design and engineering. Selecting appropriate resources is important for mastering this skill. Several books cater to different levels of expertise, ranging from beginner-friendly guides to comprehensive references for advanced users. For beginners, consider Electrical Load Calculation Made Easy by Bill Nye. This book offers a concise and straightforward approach to understanding the basics of load calculations without overwhelming technical jargon. Another excellent option is Simplified Electrical Load Calculation, a step-by-step guide by John Kretschmer. This book covers the fundamentals of load calculations with practical examples and exercises to reinforce learning. Load Calculation for Electrical Design by Neil Gerber provides a more in-depth exploration of the theory behind load calculations. It also offers detailed guidance on various types of electrical systems. Electrical Estimating and Load Calculations by Paul Rosenberg combines load calculation principles with practical estimating techniques, which can be beneficial for those involved in project costing. Simplified Electrical Design and Load Calculations by Asimbati serves as a user-friendly guide that explains complex concepts in a clear and accessible language. For intermediate to advanced users, Electrical Design and Load Calculation by William Vigras is a comprehensive reference covering advanced topics like power system analysis and harmonics. The National Electrical Code Handbook by Charles Tabor is another invaluable resource. It includes detailed tables and formulas for load calculations along with National Electrical Code, or NEC, code requirements. Chapter 28 of the ASHRAE Handbook Fundamentals provides in-depth information on heating, ventilation, and air conditioning, or HVAC, load calculations, covering heat gain, heat loss, and equipment sizing. In addition to books, several online tools and software programs can simplify load calculations. The Electrical Loads Calculator, offered by the International Electrical Testing Association, or NETA, is a free online tool that simplifies load calculations for residential, commercial, and industrial applications. Load Calc by Schneider Electric is a software program that automates load calculations and provides comprehensive reports. When performing load calculations, it's crucial to follow a systematic approach. Firstly, gather all the necessary information, including the voltage, amperage, and power factor of the loads being considered. This information is typically found on equipment nameplates or in manufacturer's specifications. Secondly, determine the type of loads. Loads can be classified as either continuous or non-continuous. A continuous load is defined as a load that operates for 3 hours or more. Non-continuous loads operate for less than 3 hours. Thirdly, apply the appropriate demand factors to the loads. Demand factors are used to account for the fact that not all loads will operate at their maximum capacity simultaneously. Demand factors are typically provided in the National Electrical Code, or NEC. Fourthly, calculate the total connected load by summing up the individual loads after applying demand factors. Fifthly, determine the size of the service entrance conductors and overcurrent protection devices based on the calculated load. This involves consulting the National Electrical Code, or NEC, tables to select the appropriate conductor size and overcurrent protection rating. The National Electrical Code, or NEC, provides specific guidelines for calculating electrical loads for various types of occupancies and equipment. Firstly, for dwelling units, the National Electrical Code, or NEC, Section 220.12 requires a general lighting load of 3 volt amps per square foot. This value accounts for the power consumption of lighting fixtures throughout the dwelling. Secondly, small appliance circuits in dwelling units, as per National Electrical Code, or NEC, Section 220.14H, must be calculated at 1500 volt amps each. This includes the 2 required small appliance branch circuits for the kitchen and 1 laundry circuit. Thirdly, for ranges and cooking appliances, National Electrical Code, or NEC, Table 220.55 provides demand factors based on the number and rating of the appliances. These demand factors reduce the calculated load to account for the diversity of cooking appliance usage. Fourthly, air conditioning and heating loads are calculated based on the equipment's nameplate rating. The National Electrical Code, or NEC, Section 220.60 allows for the smaller of the heating or air conditioning load to be omitted when calculating the total load. Fifthly, for non-dwelling occupancies, such as commercial buildings, the National Electrical Code, or NEC, Section 220.12 specifies different lighting load requirements based on the occupancy type. For example, office buildings have a lighting load requirement of 3.5 volt amps per square foot, while retail stores have a requirement of 3 volt amps per square foot. Sixthly, receptacle loads in non-dwelling occupancies are calculated based on the number of receptacles and their intended use. The National Electrical Code, or NEC, Section 220.14a requires a minimum load of 180 volt amps for each receptacle. Seventhly, motor loads are calculated based on the motor's horsepower rating and voltage. The National Electrical Code, or NEC, Table 430.248 and 430.250 provide full load current values for alternating current, or AC, single-phase and three-phase motors, respectively. Eighthly, for electric vehicle, or EV, charging equipment, the National Electrical Code, or NEC, Section 625.14 requires that the load be calculated at 100% of the maximum charging current. Ninthly, when calculating feeder and service loads, demand factors can be applied to account for the diversity of loads. The National Electrical Code, or NEC, Table 220.42 provides demand factors for various types of loads, such as lighting, receptacles, and appliances. Tenthly, it's essential to consider future load growth when calculating electrical loads. It is advisable to add a safety margin to the calculated load to accommodate any potential increase in demand. The National Electrical Code, or NEC, provides guidelines for calculating voltage drop in branch circuits and feeders. Firstly, the National Electrical Code, or NEC, Section 210.19a on Informational Note 4 recommends that the voltage drop in a branch circuit should not exceed 3%. Secondly, the total voltage drop from the service entrance to the farthest outlet should not exceed 5%. Thirdly, voltage drop calculations are based on the conductor's resistance, the length of the circuit, and the current flowing through the conductor. Fourthly, the National Electrical Code, or NEC, Chapter 9, Table 8 provides the alternating current resistance and reactance for conductors. Fifthly, to calculate voltage drop, use the following formula: voltage drop equals current times resistance times length. Sixthly, for three-phase circuits, a factor of √3 is included in the voltage drop formula. Seventhly, increasing the conductor size can reduce voltage drop. Eighthly, using conductors with lower resistance, such as copper instead of aluminum, can also reduce voltage drop. Ninthly, minimizing the circuit length can also help to reduce voltage drop. Tenthly, voltage drop can affect the performance of electrical equipment. Excessive voltage drop can cause motors to overheat and reduce the light output of lamps. Proper load calculations are critical for ensuring the safety and reliability of electrical systems. Accurate load calculations help prevent overloading of circuits, which can lead to overheating, insulation breakdown, and electrical fires. Overloaded circuits can also cause equipment malfunction and reduce the lifespan of electrical components. Proper load calculations also ensure that the electrical system can handle the expected demand without experiencing voltage drops or other performance issues. Regular review and updating of load calculations are necessary to accommodate changes in occupancy, equipment, or usage patterns. Changes in occupancy can affect the lighting, receptacle, and appliance loads. New equipment additions or replacements can also impact the electrical load. Usage patterns may change over time, leading to variations in demand. The use of energy-efficient equipment can help reduce electrical loads. Replacing incandescent lamps with light-emitting diode, or LED, lamps can significantly reduce lighting loads. Using energy-efficient appliances and motors can also help lower overall energy consumption. Implementing energy management strategies, such as load shedding and demand response, can help optimize electrical loads. Load shedding involves temporarily reducing or disconnecting non-essential loads during peak demand periods. Demand response programs provide incentives for customers to reduce their electricity consumption during peak demand events. Consulting with a qualified electrical engineer or contractor is recommended for complex load calculation scenarios. An electrical engineer can provide expert guidance on load calculations, system design, and compliance with applicable codes and standards. A qualified electrical contractor can perform the necessary electrical work and ensure that the system is installed safely and correctly. Understanding the fundamentals of electrical load calculations is important for anyone involved in electrical design, installation, or maintenance. Proper load calculations ensure the safety, reliability, and efficiency of electrical systems. By utilizing the resources and techniques discussed, one can master the art of load calculations and contribute to the creation of safe and efficient electrical installations. Remember to always consult the latest edition of the National Electrical Code, or NEC, and other applicable codes and standards for the most up-to-date requirements and guidelines. Also, regularly update your knowledge and skills through continuing education and training programs.